All right. So today we're going to be talking about multimodal learning. Talk a little bit about what multimodal learning is and why we do it. We'll talk a little bit about CLIP and that specific flavor of multimodal representation learning. And at the end, we'll talk a little bit about the downstream uses of CLIP. What can you do with CLIP once it has been trained? So to start off, what is multimodal learning? So we should start by talking a little bit about what multimodal is in the first place. There's many different ways to represent the same kind of object. On the right side of the slide, you can see we have two different sets of text, the gray squirrel, the red squirrel, and three different images of a squirrel, all in a very similar pose, similar features. So this sort of describes that we can have text representing our objects. We can have images of the object. We can also have video of an object, someone talking about the object, an audio clip of them talking about it, or the object itself making noise, right? So there's different ways in which we can represent with data the same kind of thing. And even objects that are of the same data type can all have little permutations. As you can see, these three different images of a squirrel are different in their style and the way in which the object is drawn, right? Not all squirrels are the same. The way in which we represent all of these can be similar, but hopefully it also captures a little bit of the nuances. It sort of harkens back to what we were talking about earlier in the semester with word embeddings, where the objective was to take similar words and map them in a latent space to points which, if the meaning of the word is similar, is closer in distance. So to cap it off again, we have objects that are the same but can be represented in different ways, and objects even within the same data type that are different. And we would like to capture these nuances somehow, as well as still capture that the object is the same. So for multimodal datasets, our datasets might come in many different forms, right? So, we've talked a lot about image datasets throughout the semester where we have pairs of images and class numbers. We can also have text datasets, like on the right-hand side, where we have raw text. Oh, I'm sorry, I jumped the gun a little bit. We can have text datasets with raw text and potentially, sentiment labels or translations. We can have audio datasets similar to text datasets, right? Video datasets. And we can have datasets with any combination or pairs of the data types enumerated above. So we can have perhaps image caption pairs or video audio pairs. Like on the right-hand side of the slide, you can see pairs of images with corresponding captions. The first image is a picture of a gray squirrel, and accordingly we have the caption, the gray squirrel. On the bottom, we have a red squirrel and the caption, the red squirrel. And even if you have image class number pairs, you can sort of create trivial captions, even like an image of, and then insert whatever the object name is. And with self-supervised pre-training, as we talked about previously, we never really paid attention to whether or not, even if these labels existed, what could we do with them? We always just threw away labels or any extraneous data corresponding to all of our images, because in self-supervised learning, the goal is simply to figure out, or at least in the kinds of self-supervised learning we talked about, the goal is simply how do we learn from just unlabeled images. But oftentimes throwing away all this extraneous data, might result in less information. So is this really optimal to be throwing away all this extra data? That's sort of the concept of multimodal data sets, is we're going to keep all of this information, all these pairs of images, captions, all these pairs of video, audio, all of this, keep everything. So let's talk a little bit about why multimodal learning, why is this a problem we really care about? So our data can come from lots of different places and lots of different data sets. Like we've talked about ImageNet, but there exist lots of other data sets, some presumably that have images that are more cartoon-like some of these other images of squirrels that we have. Some are photorealistic, some are cartoons, some are sketches. Different data sets might contain entirely different objects too, right? ImageNet has 1,000 different classes, but I'm sure there are other data sets that contain entirely different objects that are not an ImageNet at all. And, furthermore, ImageNet is a data set, of objects like this first squirrel, where the object is, front and center, never really containing more than one object, right? So we refer to these different, changes, these differences between data sets by referring to each data set as having a distribution over possible images. So if we have a photorealistic data set like ImageNet, it's highly unlikely, it's very improbable that it contains an image like the ones on the bottom of the slide, where it's either a sketch or cartoonish. So we can think about every single possible image has like some probability of being inside this data set. And if it's like a photorealistic data set, then, it's probably low. It's probabilistically unlikely that, there's a cartoonish image. So each individual data set's distribution frequently in machine learning is very small compared to what's possible. Like we'll have data sets that are of photorealistic images, or we'll have a data set specifically for cartoon images. So let's talk about why this is important to bring up. Distribution shift becomes a really big problem. So if you have a computer vision model that was trained on maybe photorealistic data like ImageNet, and you say like, okay, how well does it do at identifying what this image of a squirrel that's been hand-drawn, sketched? If we evaluate our computer vision model on sketches, it's very likely that we're going to do very poorly. And this is suboptimal. I mean, this image is clearly recognizable as a squirrel to any human. We'd really like our computer vision models to generalize to all kinds of data. And we refer to this problem again as distribution shift, in that if we train on a distribution of images that is more likely to be real than not, where if we shift over, if we test on a distribution of data that is more likely to be cartoonish than not, we have shifted the distribution of data, and we're going to do very poorly. So this is a problem that we'd really, really like to solve. This is the problem with regular learning that multimodal learning is sort of trying to aim at, in essence. So in the wild, across the internet, across all the different types of data sets that exist, there's incredible data diversity. We have images of different kinds, different styles, all over the internet, with all different kinds of objects in them. We have so many different data formats. We have images, we have video, text, audio, everything. And we also might have different relationships in each data between bits of data. Some data sets might have pairs of images and object numbers. Others might just have raw images. Other data sets might have pairs of images and captions. Others might have pairs of video, audio, etc. And not even to mention again that we can make captions trivially for, if we have an object number, we can create text from audio, we can create images from video. So there's all these different kinds of relationships that we can have. The goal of multimodal learning is to figure out how do we use all of these different representations between the data. How can we throw away nothing? Instead of what we used to do, which is strip the data sets for specifically the kind of data that we were interested in. In self-supervised pre-training for image, computer vision models, we frequently just strip data sets to get unlabeled images. And that's not necessarily ideal. And the hope is that by using all of this data, we can train on more diverse data, train better models, what's more, from more diverse data. And, by virtue of the fact that we're using every relationship between every single bit of data in our data set. Similar with representation learning, our goal is going to be to learn meaningful compressed representations, at least in the context of this slide deck, of hopefully, everything, images, text, audio, video, everything, meaningful compressed representations. So to sort of sum it all up, right? We have data that comes all different kinds of, forms with different relationships, text, video, images, audio, perhaps paired, with relationships like text corresponding to the video or audio corresponding to the video, text corresponding to an image, all of this. It's also, important, we have different kinds of data even within data sets. Our data sets are as diverse as they can be. There's still a very small segment of what's possible. Every data set that exists is a very small slice of all the images that are possible in the wild that you might encounter just perusing the internet, right? Models trained on one distribution will frequently struggle on new distributions. How do we go about learning compressed representations in a way that benefits from relationships that we have between different pieces of data? So this is sort of what multimodal learning is. This is what we're going to try and tackle with the flavor of multimodal learning, the paper that we're going to be tackling here. This paper is called CLIP. So CLIP stands for Contrastive Language Image Pre-training. It's a relatively new paper, although with how fast ML moves, even a paper from 2021 is still fairly old. And this paper looks specifically at relationships between images and text. You can think about like Instagram, where we have lots of image caption pairs that are very common in the wild. And if we have image data sets with object labels, we can also create some basic captions to sort of give us more data to work with, more image caption pairs for our data set. And in this paper, they combined it with a very, very large data set of images and captions to get a ton more data than you could get from any one data set, ImageNet or whatever. They had an enormous amount of image caption pairs from all over the internet with all different kinds of images in them, all different styles, all different modalities. And the basic idea with CLIP is that if we have images corresponding with captions that they are attached to, the representations learned for both the image and the caption should be the same. So we talked before about image encoders and a little bit about text encoders. We're not going to worry about architectural details here. We're just going to black box just something like a vision transformer and then like a transformer that's made for like, natural language. Takes in a sentence, or in the case of our vision transformer, takes in an image and outputs some fixed latent vector, like 128 dimensional, 512 dimensional, whatever. Takes in an image, and our language encoder takes in text, and both of them output something like a 512 dimensional latent vector. The idea is that if our image, if we take the latent representation of our image and we take the latent representation of the caption, we would like them to be the same because the caption describes the image. They should be semantically very similar. So ideally, the learned representation should be the same too. And this will be despite the fact that the images are getting passed into one model and the text is getting passed into an entirely different model, I should note. These are not the same model. These are two different models. We have one for text and we have one model for processing images. We want to compare and contrast all these different pairs, asserting that matching image caption pairs have similar representations and different image caption pairs have representations that are very far apart. Again, to note, there's no model or architectural innovations at play. We're just going to black box language transformers and vision transformers, training them from scratch. So here's an image of what CLIP is doing and sort of the training procedure. So let's look just first here at step one. And this is directly from the CLIP paper. So step one is really the meat of it. We're going to be pre-training both the text encoder, which is again just like a transformer for natural language, and our image encoder, which is another just a vision transformer. Both of them initialized from scratch. So what we're going to do is we're going to take a bunch of image caption pairs. So you can see on the left-hand side, we have a caption Pepper the Aussie pup, which corresponds to the first image in the stack, which is an Aussie pup, presumably named Pepper. We have a whole bunch we have n different pairs of images and captions. We're going to take all of these images and pass them through our image encoder to get a bunch of 512 dimensional, or however many dimensional embeddings for one for each image. You can see that's where I1, I2, I3 up to IN comes from. Same thing for text, which is going to give us 512 dimensional latent embeddings, T1, T2, T3, all the way to Tn. Now remember, T1 and I1 came from an image caption pair that matches. So ideally, if our latent representation of I1 is similar to T1, the dot product between the two latent vectors, because the vectors ideally are very similar, the dot product between them is going to be very large. And ideally, if, say, we compare T1 and I2, a caption that does not correspond to the image, so the caption does not describe what is in the image. If we take the dot product of these encoded representations of the image and the caption, they should be very dissimilar. They should be hopefully even orthogonal to one another. And the dot product between the two should be very small, or negative perhaps. They should be very, very far apart. And the same thing goes for any other image caption pair. So you can see along the diagonal are embeddings for image and the text that are the same. So in the top left-hand corner is the dot product between our matching pair I1 and T1, which is the embedded version of the Aussie pup named Pepper and the caption saying Pepper the Aussie pup. And the second element along the diagonal, I2, T2, is the dot product between our image embedding and our text embedding, or our encoded text and image text, I should say. Our encoded text and encoded image. The dot product is hopefully very large because the image is the same as what is in the text. And hopefully our image and text encoder learn to output, embeddings that are very similar if what they contain is, about the same. So every element along the diagonal corresponds to a pair, the dot product between a embedded image and embedded text pair. Everything not along the diagonal corresponds to things that do not match, things that we'd hopefully like to be very small, given that these two embeddings are very far apart, hopefully. What we're basically going to do is look at any given, let's say just look at a column for now. The first element corresponding to the correct pairing is very large, and ideally everything else is very small. It's very similar to a classification task almost, where the output of our neural network is a whole bunch of logits, and we'd like the logic corresponding to the correct class to be very large and all of the other logits to be very small, after which in image classification, we softmax and then just take a binary cross entropy loss. So that's what we're going to do is we're literally just going to look at this first column. We're going to say, okay, the correct label for this column is logit 0. And we're just going to take the binary cross entropy loss. We're going to do the same thing for the second column where the correct label is at index 1 and so on and so forth. You'll also notice you can do the exact same thing for the rows. Just again, do a cross entropy loss where the correct logit of the first row is the 0th index. Look at the index 1 row and set the correct label to be at index 1, cross entropy loss, which has the effect, again, this loss function, of taking these elements along the diagonal and trying to make them as large as possible. The encoder for text and the image encoder are going to work together to try and get these elements along the diagonal as big as possible, meaning these two models, the text encoder and the image encoder, are going to work together to make the dot product between matching elements the same and non-matching elements very small. It's the basic idea. We have a text encoder and an image encoder that are working together to spit out the same thing if they have a true pair of data. And at test time, if we want to do some classification on a new image, we're going to say, okay, so this image that we're about to pass in could be one of the following. It could be a plane, could be a car, could be a dog, so on, could be a bird. We're going to create dummy little captions that say just a photo of a plane, a photo of a bird, a photo of a car, a photo of a dog. We're going to pass all of these fake little sentences, these captions, that we've come up with through our text encoder to get different embeddings. So if the image is indeed a photo of a plane, it'll probably match the first text embedding, T1. If the image is in fact a photo of a car, it will probably match T2. I should note I'm looking at this section here on the right, section 2, create dataset classifier from label text. So on and so forth. If it's an image of a dog, it's probably going to match the label T3. If it's an image of a bird, it's probably going to match TN. We're going to pass the image I through our image encoder. We're going to take the dot product of that encoded image, I1, with all of our different captions, which is going to tell us how similar is our image to all of these different captions we created. We're going to see that our image, after being encoded, creating I1, it's going to be very similar to T3 because the third caption we created was the caption, quote, a photo of a dog. Because our text encoder and image encoder have worked together to output the same thing when, the caption matches the image, we're going to observe that I1.T3 is very large and everything else is very small. And because our photo most closely matches the text embedding, a photo of a dog, we're going to assert that the image in question is a dog. This is called zero-shot prediction. And it's going to be used to show that, after we've trained our text encoder and our image encoder to output these 512 dimensional vectors that supposedly represent our image in this latent space, it's going to show that these vectors, these encoded representations of text and image, are extremely meaningful. If we can correctly classify things in a zero-shot manner, meaning with no fine-tuning, with zero fine-tuning whatsoever, if we can correctly classify a new image that we have never seen before, it's going to show, how powerful is this method. So that is basically the overview of CLIP in perhaps more detail than I needed. The most important things being, CLIP takes two models, an image encoder and a text encoder, and tries to make it so that the image encoder and text encoder output the same 512 dimensional vector when the inputs match Pepper the Aussie pup and a picture of said Pepper. And, dot products are very small when the two things in question do not match. So again, it's just a black box division transformer and a black box language transformer. The only unique thing that's happening here is the way in which we formulate our loss function, trying to push things that are the same very close together, pushing things that are different very far apart. And this is some of the pseudocode that was included in the paper. Take an image, a bunch of images, take a batch of text that corresponds to said images, and basically just do a cross-entropy loss on all the rows and all the columns where the correct answer is all of the blue elements. The correct thing in which we're trying to sort of, in this case, classify as blue, and all the incorrect elements are in white. Yeah, so that is what CLIP is. It's basically a clever scheme to take data sets with matching text and images and trying to learn latents from them that are going to be useful for classification or perhaps downstream tasks. It's trying to learn a meaningful representation of text and images. So does this work? What are the effects? So what we observe is that CLIP features are extremely robust to domain shift, since CLIP is trained on such a wide variety of data. It basically means you can generalize extremely well. So CLIP features can be used to classify images, as we see on the right-hand side, with extremely high accuracy, considering that we have no fine-tuning going on. So on the right-hand side, we are looking at like fine-tuned classification of a ResNet 101 model that was pre-trained on ImageNet. And on the right-hand side is the zero-shot CLIP in this column over here. So ImageNet accuracy on data it's never seen before is really bad. It's not good. For like sketches of bananas, only 25% of the time does it really get it right. Whereas Clip, which was pre-trained on such a wide variety of data, generalizes extremely well and without any fine-tuning, whatsoever. We can still get like 60% accuracy on these sketches of bananas. Again, with no fine-tuning, which is extremely impressive and shows you just how generalizable all of these latents that we've learned are. And zero-shot prediction is even competitive across just a ton of different data sets. So this diagram, again, compares a linear layer trained on top of a pre-trained ResNet 50 compared to zero-shot Clip latents. You can see that even on like ImageNet, something as complex as ImageNet, Clip gets like 1.9% better performance relative to a pre-trained ResNet 50 that's been frozen with a linear layer on top. And it shows you just how general Clip latents are, that Clip latents, just again, which is just to say the output of our image encoder here, those outputs after we've frozen the model and no longer pre-train it are extremely good. They're extremely meaningful, making it extraordinarily easy to classify images or use these latents for any downstream task you could think of. So that's why this is like a really, really important idea, a really, really important paper. So talking a little bit more about downstream tasks. So we talked about classification. We can use Clip to classify objects we've never seen before, objects that come from wildly varying distributions. That's one thing we can do with Clip. Another thing you can think of is, say, robotics, where our robot has an image of the scene, and from it needs to try and figure out, where is the object? How am I going to path to it? How am I going to pick it up? We have a deep decision-making network that needs some kind of embedded representation of the images that it's taking of this scene. And Clip latents are very useful there. If you don't want to have to learn an entirely new vision model from scratch, you can just take Clip latents, just this frozen image encoder, and just use it out of the box and just pass into your decision-making network these Clip latents, and it actually works. Again, the idea of representation learning is applicable everywhere, because these latents describe these images extremely well, the content of them. And this representation learning idea is sort of at the core of like text to image generation, things like stable diffusion. So it's basically everywhere. And just because this makes me happy, I decided to include this as well. This is also very much applicable in the world of 3D vision, where we talked a little bit about NeRFs. You can optimize a radiance field with the loss function being that we want the rendered image to match the Clip latent corresponding to an input caption that we give. So say we start with literally nothing except for the caption "washing blueberries," and we want to create an object that looks like blueberries that are being washed. What we will do is we will take this caption, "washing blueberries," put it through our Clip text encoder in purple here, put it through our Clip text encoder, take the 512 dimensional latent, compare that to what our radiance field currently is, which will start out, it'll be randomly initialized. We'll render out an image, pass the image through our vision transformer, which is, again, the image encoder here in green, pass it through the image encoder for Clip, and compare the latents. If our neural radiance field reconstruction of the object is very, very good, then the rendered image will have the embedding that will be very similar to the embedded caption. And in this way, you're going to continue optimizing your radiance field, because every single step of this is differentiable. From rendering out images, passing those images through the VIT, all of that is differentiable. So we can backpropagate from the difference between our Clip embedding and our rendered image embedding all the way back to the parameters of our radiance field. And you can see some objects that were generated. A bouquet of flowers sitting in a clear vase was the prompt given here. And this was the radiance field that was optimized. I should note this is extremely expensive to do because rendering out images with neural radiance fields, as we talked about, is not cheap. But it's I think a really cool idea that demonstrates just how universal these clip latents are. That all we had to go off of was the clip embedding for the caption, bouquet of flowers sitting in a clear vase. And we were able to generate, a neural radiance field whose rendered images also, after being passed through our image encoder, give us latents that are the same. The fact that it's clearly meaningful, the fact that it clearly works is pretty incredible. So that is the overarching idea of CLIP. We have, because we trained on such a wide variety of data, because we used representations or relationships between different representations of the same bit of data, captions and text, because we utilized all the information that was available to us, and pre-trained on such a wide variety of data, we have these latents generated for any sentence or for any image that are basically usable out of the box in any possible domain. So that is what CLIP is. That's why it's important, and that's some of the use cases of it. Multimodal learning is obviously much larger than just CLIP, but it's definitely one of the places where this subfield, I should say, really came to life. And it's definitely one of the more important papers. Since then, things have obviously evolved, but this is sort of the OG for multimodal representation learning. So yeah.